So in topic 29, we looked at amino acids as the building blocks of proteins and polypeptides. We're going to have a closer look at amino acids here now. So we know that amino acids are the building blocks of proteins and polypeptides, which are essentially the building blocks of all living things, really. So this is why it's important to know the structures of amino acids. There are about 20 important naturally occurring amino acids, and they are all what were called alpha amino acids. You've got to know what an alpha amino acid is as well. And we sometimes call these alpha amino acids 2 amino acids. And we've got to have a look at the structure of an alpha amino acid to understand why we call them 2 amino acids. So here's our amine group. And here's our carboxylic acid group. So it's an amino acid. Okay. Now, what we've got here is we've got an amine group on a carbon next to the CO2H group. And that's why we call them 2 amino acids, because the amine group is on the second carbon. This is carbon 1, and that's because the carboxylic acid group takes priority. This is carbon 2, and the amine group is on carbon 2. This is called a 2 amino acid. The next thing to note, at this particular carbon here, carbon 2, the one I'm going to put a little star on here, you might have seen this little star before when we looked at chirality, is attached to 4 different groups. This carbon here is attached to 4 different groups. 1, 2, 3, 4. So we've got an amine group, a carboxylic acid group, a hydrogen, and then whatever that could be, that R group. It's usually a CH3 or a CH2, CH3, it could be a benzene ring, it could be anything, to be quite honest. And there's naturally 20 naturally occurring versions of this structure. And the only thing which changes is this R group here. So all 20 naturally occurring amino acids have an NH2, an H, and a carboxylic acid, and it's just this R group which changes. And because we have 20 versions of this with 20 different R groups, then if it's chiral, you have 2 different versions of that amino acid. Now, in reality, in the natural environment, we only ever see 1 enantiomer of that naturally occurring amino acid in nature. So there would be 40 different amino acids in theory, because you've got 2 enantiomers of each of the 20 amino acids, so 20 times 2 is 40. However, in nature, we only ever see the negative enantiomer. So we have a positive version and a negative version. Depends on how those 4 groups are arranged around the central carbon atom, which is chiral. So that it's the positive enantiomer, the negative enantiomer, which is naturally occurring, and it's a positive one that we don't normally see. So negative enantiomer is naturally occurring. Okay, so let's have a look at some of those naturally occurring amino acids. So let's have a look at this one. You might have, in your biology, you might recognise this one. There we go. Now, that one is often abbreviated like that, and this is what it looks like. the R group is a CH3. So this R group here is a CH3. You could draw it like that if I want. There we go. That's alanine. You might have heard of this one as well. Glycine. And that's abbreviated GLY, like that. And this time the R group is a hydrogen. Now this is the only one which doesn't have a positive enantiomer and negative enantiomer. So, and this is because there's only 3 different groups attached to that carbon there, because that's actually a hydrogen, which is the same as this one. So this one's not chiral. It's the only one that's not chiral. It's obviously chiral because it's got 3 different groups. 1, 2, 3, 4 different groups. Let's do another one. Got this R group here. That's valine. You don't need to learn the structures of these. The only one that I want you to learn is this glycine one. But you need to know the general principle here of the fact that this R group changes and you get different amino acids. Okay. So the systematic name of glycine is 2-amino ethanoic acid. Ethanoic acid because you've got 2 carbons here and there's an amine group on the second carbon, so it's 2-amino ethanoic acid. Okay. Okay, so let's have a look at the acid and base properties of amino acids. And because they've got an acidic functional group and a basic functional group, they can act as an acid or a base, or both. So this is acid and base properties of amino acids. So let's just have a look at part of the molecule. Let's just have a look at the carboxylic acid group of the molecule on an amino acid. I'm not going to draw the rest of the amino acid, I'm just going to draw the carboxylic acid bit. So there's our carboxylic acid bit, like that. Now the carboxylic acid group has a tendency to lose a proton. Now something which loses a proton, or donates a proton, is an acid. So let's donate a proton. So that's going to be this proton here, isn't it? What's generally found though is an equilibrium here. Remember, this is a weak acid. Carboxylic acids are weak acids. There we go. So the carboxylic acid can lose a proton. It can essentially act as an acid. Here, the amino acid is acting as an acid. That's how they do that. Let's look at the other end of the molecule. The other end of the molecule, what you've got is this amine group. Now, the thing about the amine group is you've got a lone pair of electrons on that nitrogen. And because you've got a lone pair of electrons on nitrogen, it can actually act as a base. And a base is something which accepts a proton. Here's my proton on this side of the equation this time. So it can accept a proton. And remember, amines are weak bases, unlike hydroxides, like sodium hydroxide. Therefore, it's an equilibrium again. There we go. So this is showing how an amino acid can act as a base. Okay, so this is how an amino acid can act as an acid. This is how they can act as a base. So let's draw an amino acid. So the amino acid I'm going to draw is, I'm going to do this one. And we know that this particular one is glycine. There's glycine there, where the R group is actually a hydrogen. It's non-chiral this, because you've got two atoms which are the same there. There's only 3 different groups attached to that carbon there. So it's not chiral, so I'm not going to put one of those little stars there like that, but it's the most simplest one I can use. So let's show how glycine can act as an acid. So glycine can act as an acid by taking this hydrogen off here, okay? So we can deprotonate it. There we go. So we can deprotonate it here, like this. Now, let's have a think about when it would be deprotonated. So it would be deprotonated in alkaline solutions. So in alkaline solutions, this would be the structure of the amino acid. So in alkaline solutions, it would be deprotonated. So in alkaline solutions, the acid, the amino acid, acts as an acid. So it acts as an acid by donating a proton in alkaline conditions, because acids and alkalis react. So that's one thing that it can do. So we can deprotonate. So deprotonate is when it acts as an acid in alkaline conditions. We can also protonate it. So if we protonate it, it's actually acting as a base. By accepting a proton. Let's have a look over here. So what we're doing is we're adding an H plus to the NH2 group here. So I'm just going to copy down my original glycine molecule here, first of all. And then I'm going to add a proton to this nitrogen here. There we go. Like that. Okay. So, amino acids, when you find them in a bottle, you don't normally find them like that. Yeah. Amino acids exist as something called Zwitter ions. Okay. And Zwitter ions are ions that have both a permanent positive charge and a permanent negative charge, so that the compound is neutral overall. So let's draw the Zwitter ion of this structure here. So a Zwitter ion, essentially what we've done is we've taken a proton off here, so we've deprotonated it here, and put that proton on here, so protonated it and deprotonated it at the same time. Alright, so the Zwitter ion, this is how you spell Zwitter ion, of glycine looks like this. So I'm going to get to that point there. I'm not going to put the hydrogen on here. I'm going to put a negative charge on instead. And I'm going to put that proton here. So this is an ion. However, it's an ion, but it's got no overall charge, because it's got a positive and negative there, going to cancel each other out. Now, this bitter ion actually has high melting points, okay? And it behaves a bit like an ionic salt, okay? Like sodium chloride. So it behaves more like an ionic compound rather than something which is covalent. So these have got an overall charge, they have high melting points, just like any other ionic compound. And you usually find them is a white solid. So if you buy a tub of particularly amino acid, then if you were to look at this structure here, you'd go, oh, it's probably going to be a liquid or maybe a gas or something, maybe a liquid, but actually it's not. If you take the top off it, you'll find that's actually white solid. And the reason why that is because actually what's inside that tub is the bitter ion, okay? So what we've done is we've basically deprotonated it and protonated it at the same time, okay? And that's what bitter ion is. And so properties of bitter ions, high melting points, they're solids at room temperature, and they dissolve well in water as well, okay? And the reason why they dissolve in water is because they've got a positive and negative end there, and they won't dissolve in non-polar solvents, so like something like hexane or something, they won't dissolve in non-polar solvents. So they only dissolve in water or polar solvents. So they're insoluble in non-polar solvents. Okay, a bit like sodium chloride. Salt would not be soluble in likes of hexane because it's non-polar. All right. So this is interesting now because what we've got here is we've got an amino acid which you can deprotonate and act as an acid in alkaline conditions, or you can protonate it and act as a base in acidic conditions. Add that on there. And it exists normally as its bitter ion. Right, what I want you to do now, this is your task. There's two parts to this task. The first task is all about this amino acid here, alanine, and the second task is all about valine here. All right. What I want you to do for both of these amino acids, this one and that one, and do for both of these, I would like you to show me what the structure would look like in alkaline conditions. And that's when it acts as an acid, when you deprotonate it. I want you to draw the structure of what it looks like in acidic conditions. That's when it acts as a base, where you protonate it. And also the structure of what it would look like as a zwitter ion, and then write down the properties of that particular zwitter ion as well. All right. So what you're going to do now is you're probably going to set out your page very much looking a little bit like this, and you'll do it for this amino acid and that amino acid there. Okay. And that is your task for this part of the lesson.